Okay, so the next step in the process is after we made the scatter plot and we found the correlation coefficient, now it's a question of making the line of best fit, which is also known as the regression line or the linear model, right? Or along the least squared regression line, essentially. So what makes it the best line? Because there's lots of lines I could draw through the data, right? But who's to say which one is the best one, right? So you have the line which you create, right? Which is called the model, which makes predictions. And then you have the observed points, which is the data you collected, which are above and below that line. So if it's below the line, this has a negative residual. And if it's above the line, it has a positive residual. A residual is the difference between the observed and the expected value. The observed and the expected value. So the goal is for every one of these residuals, you want to minimize them, right? So if you, as you move the line, right, if I move this line down, it would decrease this residual. But if I move the line down, it would increase this residual here. So depending on how you move the line, it's going to give you more positive or more negative residual for each one of the coordinates. So the least squared regression method gives you the best line based on all of the residuals, essentially. Okay, so talking about high school algebra versus statistics. So they did perfect models in high school. They did y equals mx plus b, but with slope and all that, you know what I'm saying? So you calculated slope and you drew slope and all that. But the reality is that statistical models are not perfect, right? And we use this right here, okay? So you're going to see it in a couple different ways. Let me just bump this down. So what you're going to see is y equals a plus bx, right, times. So the modern way of doing it is you put the little hat above it, okay? The old way of doing it is this, okay? So when they in the typewriter era, when they used to make things with typewriters, you couldn't make that little hat above it, so they did the little single exclamation there, okay? In the handwritten era and in the modern era, they used the little hat above it basically, because this means it is a sample model, right? If you used y, that would mean it's a population, which means you have all the data. Typically, you're not going to have all the data. So this is an estimation, because the model is not perfect because you do not have all the data, right? It's a predictive model, right? So it's a prediction, basically. That's why you have the little hat. So either one of those is fine. Typically, you use the y hat, but if you don't have that, then exclamation is fine, which is probably what they use in the spreadsheet. Okay, so a couple guidelines is obviously the data has to be randomly selected, stuff like that. It has to basically fit a linear model when you do the graph. You also have to worry about a thing called extrapolation, which we'll talk about later on. So the example I like to give is if you go out and collect data on healthcare costs for adults in their 20s and their 30s and you make a linear model with it in a scatter plot, you can't then use that model to make predictions about 5-year-olds or 80-year-old people, because those age groups are well outside your data set. That would be extrapolating. You're trying to extrapolate meaning for something that's well outside your data set. So any prediction you use or do has to be within the data set range of values, basically. So you can't do that, right? So there's a variety of ways they represent the linear model regression. They either use this one or this one typically. So the one on the right is what your book uses with the A and the B. Sometimes books use B0 and B1. Typically in your Stats 2 book they'll use this, but in the Stats 1 they tend to do this. And there's a variety of ways to calculate A and B. We're going to use the summation method to keep it consistent with the correlation coefficient. Okay, so what we want to do here is we want to calculate the A and the B for all three data sets essentially. Okay, so I'm going to go to our spreadsheet. I'm going to go back to 12.3 here, and I'm going to paste in the A. Shrink that down. And then we'll also steal the b here. And we'll shrink that down. Okay. So what we want to do is the a equals and b equals. And shift that to the right. And then we're going to copy, paste, and copy, paste for all three data sets essentially. Okay, so this is a little bit easier than the correlation coefficient because all I have is a numerator and a denominator, and that's it, right? So essentially, it's the same summations. You just have a numerator and the denominator, basically, right? One goes into one goes into the other. Call it a day. Okay, so let's put those data values in there. All right, so the first thing here is y times x squared minus, we have x times xy. Okay, and in the bottom I have n times, that was an x squared, minus x to the second power. And this is a mistake that, again, with r squared and with a and b people make, right? Because they think this and this are the same thing, and it's not, right? Because this is x squared, right? And this is the x to the second power, which is not the same value. You can test it for yourself, okay? All right, turn that off. I'm going to hit enter and get our value there. There's our a. So then I'm going to do my b, numerator divided by denominator, right? So my numerator is n times the xy minus the x times the y. And on the bottom, I have n times x squared minus x to the second power. Okay, and there's my b value, essentially. So I'm going to cheat. I'm going to copy this, paste it here. Okay, so the only thing I have to change now, I need to change these to 18 for mine. 18, 18, 18, 18, 18, and 18. And that one still maps to the 7 there. Okay, and map this to 18, 18, 18, 18, and 18. So now it's all the orange ones down there, right? Okay, and we'll do that again. We'll copy and we will paste. Okay. Now I want to map to what? 31. So map to 31, 31, 31, 31, 31, 31. Right, so that maps all to my orange ones down there and the 10 still. And this one needs to be 31, 31, 31, 31, and 31. Perfect. Okay, so there is our models essentially. So this is y hat equals, right, 0.39 plus 0.106x essentially, right? Although there's some decimals in there, right? Okay, and we can probably make this bigger, right? Make that a little bit bigger. Yeah, that's okay. So we'll copy those, go down to there, paste. Okay, so this one is, I don't know, 102.49, and this is minus 3.62, right? And then down here, we'll paste it again. Oops. Okay, so this is 11.79 and plus 0.105. I don't know, close enough. They keep going forever. You want to use the exact values anyways, and we do the predictions later on. Okay, so let's look at our notes here. What does the correlation tell you about the regression line? Okay, so let's think here for a minute. So if I copy and paste here. So this is our model, right? Which is you plug in cars, you get out revenue. Well, the correlation coefficient was what? It was 0.98, which is really good. So that means it's a good positive relationship, basically. So what we can say is the correlation coefficient is stating the model is a good fitting positive linear model that can be used to make predictions, right? So that equation is thumbs up good. All right, next one. The grade data, okay. We got a negative 0.94. That's also very good, okay. So what does that mean, right? That means that model is also a very good predictor. Okay, so go back to our stuff here. And we can say that this model, which is absences plugged in and grades are getting out, is a good negative linear model to make predictions. And that's what the correlation coefficient is telling me. Okay. As to how good enough is, I don't know. That's going to take inference later on. And then the last one is the teacher-pupil problem. Okay, let's see what we got here. Well, if I look, that's 0.44. That's not good. That's below 50, right? So I would say that's not a good predictor, essentially, right? So what I would say there is, yes, you can make a model. Is that model any good? I don't know about that. So yes, you can plug in teachers and get some kind of ratio out, but it's a poor fitting positive linear model that probably should not be used to make predictions. As to whether 0.44 is good or bad, we'll decide that later on. We do some inference in later sections, essentially.